Okay, welcome to lecture 6. You might recall last time we introduced for the first time the freedom and constraint topologies or FACT synthesis approach for designing compliant mechanisms. We did some examples. We're going to continue looking at FACT in this lecture, primarily focusing on getting you acquainted with well, a little bit more of the design approach, but also looking at the FACT library, convincing you that there's a finite number of them, of these freedom and constraint space pairs, and getting you familiar with their geometries. Okay, and then introduce a few other concepts that are of interest here. So, okay, so first let's just review some principles of FACT briefly, and just basically how it works. So, as you know, there are 3 kinds of ways you can get a single degree of freedom. You can either get a rotation, a translation, or a screw that is a coupled translation per rotation. Okay, so the rotations are red, the translations are black arrows, and the screws are green. And you can see the pitch of the screw is the translation per rotation. So it's how much it translates up here versus how much it rotates there. Okay, of course, with FACT, you can design multi-degree of freedom systems, so things that don't just have those single degrees of freedom I showed you on the other page. This is an example we designed in a previous lecture that achieves 3 intersecting orthogonal degrees of freedom, rotations, right? And the first thing to realize is that if you get those 3, you also have to get every combination of those 3. So that's what the freedom space represents. If you get these 3, you get every linear combination of them, which is every rotation at its center. Okay, another example of a multi-degree freedom system is this one. It achieves translation and piston, tip, and tilt, 2 orthogonal rotations and orthogonal translation. But again, of course, if you get those motions, you also get every combination of those, which is represented by this freedom space. Now, in this freedom space, I did color it in red, but I did that and made it transparent and everything. Traditionally, in the FACT library and everything, I would just highlight this, outline this red. But what it means is not only can you translate with this arrow and rotate around this line and rotate around this line, but you could also get this stage to like rotate around this axis, and really any axis that you could draw on that plane. Okay? So the freedom space represents all the permissible motions generated by the independent motions, which are the degrees of freedom. Okay? In one visual picture, you can visualize how everything moves. Okay, so again, there are 26 freedom spaces, and they're organized within, or at least for parallel systems, right? And they're organized within this library that I showed you last time. You can see there's a finite number of spaces in each column. They're organized according to their degrees of freedom. You can see, on the first, the review slide I showed, here's the 3 single degree freedom spaces, and then we did these examples of the sphere of rotations and the plane of rotations of the translation, which you can see are in the 3DOF column. Okay, so all these spaces uniquely map to complementary constraint spaces, which are really pure force wrench vectors. And the reason we just look at the pure force wrench vectors is because that's all that's really pertinent to parallel flexure systems. Parallel module or parallel elements are just modeled by the blue lines that pass through their geometry, as you're familiar with wires and blades and those things. So we're really only interested in the blue space, but the motions we're interested in all 3, rotations, screws, and translations. Okay, so, and the way it works is, if you have a system that rotates, the reason is because its flexible elements all lie on intersecting planes of its constraint space, right? And the reason this works with the translation is because its blades lie on parallel stacked planes of its constraint space. And the reason this guy works is because its wires are within this guy's constraint space. And the reason this works is because these 4 blades were redundantly constrained within that guy's constraint space. So, with a knowledge of a system, a desired set of motions that you want a flexure system to achieve, or a compliant mechanism you want to achieve, you can, with a knowledge of that freedom space, its constraint space, and then you can very rapidly visualize all possible designs that even look totally different. You can see this looks very different than this last one, or this. I mean, these are all very different looking topologies. So you can wow and impress your friends with how creative you are, although you have the secret of being guided by knowing all the solutions and how to visualize them within the shape. And then, of course, how to pick them so they're either exactly constrained or over-constrained. Okay? So that's just the overview of the fact approach. And now we're going to talk more about this library. Okay? So, it might be a hard sell to remember I told you the coolest realization ever was that, there's an infinite number of parallel systems of any stage shape. You can stick the wires in at any location with any orientation. And not just to mention that, but there's also, you could use blades, you could use a bunch of other elements. There's infinite ways to do this and analyze and find the system's freedom constraint space. But I made the claim that there's only 26 of these within this library. Okay, and so now that's not immediately obvious why there's only 26. You'd think, well, if there's not infinity, maybe there should be thousands or hundreds. But why only 26? Okay. Well, and that's fortunate because it makes our life a lot easier. We just have to become familiar with 26 different things, and actually even less than that. You'll see in this lecture. Okay, so but let's do like a very rough proof of why there's a finite amount of spaces here to convince you that there's really a small amount. Okay, so say you have this rigid potato of any shape, and you just randomly, say you're playing pin the tail on the donkey or something, you just randomly stick a wire into it and ground it on its back end, okay? That would be the simplest constraint system there could be. Wire constraints are the simplest flexure constraints, and only using one. If you didn't use one, then obviously it has 6 degrees of freedom, and there's only one degree, one kind of freedom space that has 6 degrees of freedom, obviously. It's just motions in any direction. But once it becomes actually a constraint system, and you stick this in and ground it on the back, then you could go through the process of, draw the blue line, then find all the red lines that intersect it, and then find all the blue lines that intersect that. And my point is, there will really only be one constraint space, no matter where you stick that, or no matter how you orient it for this case one of just a single wire. Okay, so of course its constraint space is this blue line. And so now let's just do a little review. Using the rule of complementary patterns, can you, without, and don't check the fact space. See if you can generate yourself just to get the exercise. Can you find all the red lines that intersect this blue line somewhere at least once? Okay, you can put me on pause. Okay, assuming you did that, the answer is a bunch of intersecting red planes. So basically, any red line, rotation line that lies on planes that intersect this blue guy, so this dotted line corresponds with this blue line, they should be drawn on top of each other, would work. And that's certainly all the red lines. But of course, and we did this before, but for a red line, we found all the blue lines, right? Well, now for a blue line, we're finding all the red lines. But since we don't consider pure moments, since we just consider blue lines instead of moments and wrenches, it was just the intersecting planes of blue, intersecting blue planes. But now that we are allowed to look at translations, screws, and rotations, you can think, well, what happens when red rotation lines on these planes are pulled to infinity? Say they're parallel to this line, and then they're displaced to infinity just away from it on its plane. Well, they'll turn into beach balls of hoops, right? Each one on each plane pulled to infinity in either direction will turn into a hoop that corresponds to a translation that's perpendicular to it. Okay, so, and like I said, remember, you can think of it as a beach ball of hoops, red rotation lines, which are circles with infinite radii. that are pointing in all directions, or you could just draw the disk of translations and make it clear that that disk of translations is perpendicular to this line, which is much easier. Hoops look pretty ugly, so we do that. So again, you might recall when we had a red line, we just drew blue planes, and that's because we don't draw blue hoops. Okay, we'll talk about blue hoops later, though, in a later lecture. But they're not useful to flexure design. So we just had the intersecting blue planes. But when we go from blue line to red lines, we do need to consider the red hoops and the translations. Okay, we'd also need to. And by the way, you'd see it's freedom space right here. So here's the constraint space. It's a single wire, and its freedom space is here. It's oriented up and down. You can see the intersecting red planes, and here's the disk translation errors. There is a ton of screws in there as well. The green screws. We'll talk about those. You'll recall those are twists with a finite pitch, but I haven't shown you how to find those. So there's a bunch in there. So that's the freedom space. Okay, and by the way, we'll talk about that in this lecture, how to find the screws, right? But for now, you just need to be able to find the red lines and the black arrows. Okay, and you found those, so great. But the whole point is there's really only one type, right? You're not going to get, no matter what the shape of the stage is, no matter how I stick the stick in or the wire flexure, no matter how I orient it, its constraint space is just going to be a single blue line, and its freedom space is always going to be this. It just is a question of how you locate it and orient it. But there's not going to be another freedom and constraint space type in case one, meaning where you have a single wire, and therefore 6 minus 1 independent wire is 5 degrees of freedom. So in the 5DOF column, there's just one. So my whole point in this is, well, one, to give you experience with this, but also to prove to you that there's just one type in 5DOF column. Okay. So now let's look at case 2, where we have 2 wires. Okay. Okay. So say we stuck in the random first wire, and now say we stick in a second wire randomly. Just stick it in there. Okay. Well, that wire, no matter where these are, no matter what the shape of this is, no matter where they're stuck, no matter how they're oriented, there's only 3 possibilities that those wires could be arranged in. Okay. They could either be, and remember, let's draw them as blue lines along their axis. They could either be parallel, okay, which in that drawing they obviously weren't in the previous slide, but say I randomly stuck them in, it's possible that I could make them parallel. Okay, they could be intersecting, which it looked like, from that potato design, it very likely could be intersecting. And they could be skew, okay? So that they may not be intersecting in finite space or at infinity. They may just be in totally different planes, pointing in different directions. Okay, and they don't need to be 90-degree skew. They can, they could just be have any skew angle. Okay, well, and there's no other possibility. I mean, I suppose there's the possibility you could bullseye the wire and stick a wire, right on top of it, right through it, like an arrow on a target that splits another arrow. But if you put 2 wires right on top of each other, collinear, it's really just one wire, right? So that would just go back to the 5DOF case with a single constraint that's a single blue line. Okay, so no matter how I stuck in those 2 wires, they would either be parallel, intersecting, or skew. Hopefully, I can convince you of that. Well, but then you may say, but there's different ways things can be parallel. The distance between them could be different. And there's different ways things can intersect. The angle between them can be different. There's many different ways they can be skewed. They could be, different distance. Shortest distance between the 2 lines could be different, and their angle could be different. So the question is, by changing those things, does it change the freedom and constraint space that you generate from each of those 3 cases? Well, let's take a look. Okay, so let's look at 2 parallel lines. Just say I separate them by, I don't know, some distance h or something, right? All right, so you have those 2 blue lines. Say that was the 2 blue lines you randomly stuck in the potato. Well, find every red line that intersects all those blue lines somewhere at least once. So here's your practice part. Can you find shapes that make these freedom spaces? Okay, and remember, this time you have to consider hoops. Okay, and there might also be screws, right? In fact, there almost certainly will, but don't worry about those yet. Okay. Okay, but just find all the red lines that intersect these somewhere at least once. Well, you might think, okay, what about every red line on this plane? It's coplanar. That's this highlighted thick red plane. I might as well fill it in red because it's every single red line on that plane. That's on top of it. Okay? And then every red line in the box, that's every red line that's parallel to these two. Okay? And so that's another shape. You can see the box and the plane. And then of course, there's red lines on the plane that could be pulled to infinity. Okay, in any direction really. Okay, if you take any red line on the plane and pull it, to infinity in any direction, it will, it will make, different translations here, and same thing with the box. If you take these and pull them in any direction, it will make hoops that are again the beach ball, right? So think about it. If you take this one on this plane, pull it this way, it'll be up and down. If you take this one in the box and move it up, it'll be perpendicular to this one. And you can imagine you take red lines, pull them in any direction from the box or the plane, and you would, you would make this. Of course, you'd have to take ones from the box to get, anything translation out of this. But right, but you have the box, so you can do that. Okay, so basically, you might have found the plane in the box, but don't forget your hoops, which means your translation arrows. So that's basically a disk of translation arrows that are, their location doesn't matter. You can draw that disk anywhere because translations don't have a location that corresponds with anything. You just have a direction. The direction is this whole disk has to be perpendicular or orthogonal to these blue lines or the red lines in the box. Okay, and then there's a bunch of screws as well, but. The next question is, okay, so now that we found all the red lines and all the black lines, or the red hoops, find all the blue lines. Are there more blue lines than just these original parallel two that we stuck in that potato? Take it and you randomly stick it and you find, holy cow, they happen to be parallel. And of course, if they're parallel, they can be made to be on the same plane. Okay, and here's the plane defined by these two parallel guys. And remember, we found all the red lines that intersect them. Now let's see if there's more blue lines that intersect all those than just the two we found. And you'll find, there's infinite blue lines more, and they all lie on this infinitely large plane, and they're all parallel. So you can find, there's no other blue line outside that plane or anywhere else that satisfies the rule of complement patterns for this freedom space. So this is the constraint space. And here's the whole point, is... it didn't matter the distance between these. If I said it was h, make h anything you want, the freedom space is still going to be that, and the constraint space is still going to be that. Okay? And so that's one new freedom and constraint space type that comes anytime you make those sticks parallel, any way you want. If they're both pointing the same direction with the same orientation, right, at any location, then they're going to be parallel, and they're going to make this constraint space and that freedom space. Okay? Okay, well, what happens if they're intersecting? And say there's a specific angle here, say theta or something. Right? Well, okay, find the freedom space. Well, you find all the red lines intersect all these blue lines. Well, there's the sphere where those 2 points coincide. And then there's every red line on this plane, on this, which is shown by this thick highlighted red. And you could just color that all in red, and it's coplanar to this, and the sphere is on top there. Okay, and then of course you could pull lines in any direction from this plane, and they would make this hoop. No matter what direction you pull it, if they're stuck on that plane and you pull it out there, it's only going to all be the same line, which is a circle with an infinite radius, and it's a translation. Okay. So, and of course there's probably screws, but I haven't taught you how to find those, but. The skeleton of a freedom space is just the red and the black twists. They're pretty much everything. The screws is everything kind of in between. So just don't worry about them for now, right? Okay, but the point is now we found the freedom space. Are there other blue lines other than these original two that intersected? And the answer is yes. There's an infinite number of blue lines that lie in a disk that intersect that same point that satisfy the condition. Okay, so we've generated a new freedom and constraint space, at least so far as the second case is concerned, where we have two wires that intersect. And we've proven no matter what their angle of intersection is, if I just got these random sticks, and then let me go back here. If I just got these random sticks and stuck them in the potato, and they happen to lie on the same plane, such that they're not pointing the same direction, so they're not parallel, but they intersect somewhere, it looks like around there, then its constraint space will be a disk, and its freedom space will be that other shape I showed. Now, it doesn't matter if that disk is inside the potato or not. If these two had been like this here and I move this there, so they intersect somewhere outside the potato, it doesn't matter. The constraint space would still be where they intersect and be defined by the plane, and the freedom space would still be the same thing here. Okay, so it would be there, and it would be defined by the plane of these two, and its freedom space would be locked on top, and that would show how that potato could move. Okay, so the point is, we've just found a second freedom and constraint space type when you have two wires you're sticking in something. Okay, but what about the third way? What if I randomly stick those in, and they look like they might be intersecting, but they're on different planes, so they're actually skew. They don't actually intersect. Well, now we've got an interesting scenario. So, by the way, any two skew lines, they always have a shortest distance line that is going to be, if you draw any line that connects any point on this with any point on that, and you find the shortest distance line, that will be this dotted line that's orthogonal to both, and will define the line that's orthogonal to two planes that those lines are on. And so that's the shortest distance is the distance between those two planes, and then the angle between them. So if you project this one up and then find the angle there, that's the skew angle. Okay, and it doesn't have to be 90 as it's shown here, kind of, but it can be anything except 0 and 180 degrees, because then they'd be parallel. Okay, so but for this scenario, can you find all the red lines that intersect these guys somewhere at least once? Well, this is a lot harder to visualize, anyway, it's you might find, well, this line's an obvious one. A red line going there intersects this guy here, intersects this guy there. But can you think of a geometric shape that works? Well, the next thing I'm going to flash up is really ugly. I'm going to flash through it a little quick and go back to it. Okay, so it's really something like this. Okay, and there's two ways to look at it. These are both pictures on the left and the right. They're animating, are showing the same thing. Okay, so imagine these black dashed lines are the blue skew lines. So see the blue skew lines there, right? Well, if you imagine disks of red lines that intersect down here somewhere along this, anywhere along this blue thing, that lie on a plane that is like kind of hinging about this axis here, then every red line in that disk will intersect this blue line and this blue line somewhere at least once and satisfy the rule of complement patterns. So everything in a disk swept out like this all the way up and down the whole line, so this angle literally goes from 0 to 180, is that space. Okay, and you might say, well, what about this top one? Because this one works too, right? If you hinge this around here and use the top skew line and sweep these through, then everything in this red disk intersects, this blue line and this blue line, even though I've shown it as dashed black lines, right? But these pictures are redundant because it's the same information. If you think about it, take the single vertical red line in this disk as it sweeps out. It will construct every red line in the top disk when it's in the center right above it. Okay, and then like the next red line, this one right here, it's moving as it sweeps out, it will construct another disk angled some amount. So they're both the same information. Whether you show this, or both, it's all the same thing. Okay. Now you might say, well, wait, you said this is also true when this equals 0 or 180 degrees. Well, what happens when that disk swings up? By that point, that disk will zip out and be at infinity. And anytime you pull a disk out to infinity, similar to, remember I told you, like the rays of the sun, it's coming out of a sphere. And when the sun's really far away, those lines all hit you at parallel angles if it's infinitely far away. Well, same thing with a disk. If you pull it infinitely far away from you, it will hit you with parallel lines. So going back to this. So by the way, you can start seeing what this mess is here that I've drawn. Here's a geometric representation, all these things sweeping out the bottom one. Here's the geometric representation, all these disks sweeping out the top one. But this plane of parallel red lines is this disk swept out when it's on that plane to 180 degrees. It will come in and make a plane of parallel lines. And same thing with this one. When this one is swept out, it'll make that plane of parallel lines going the other way. Okay, and of course you can see that would work. You know, if you have red lines that are parallel to this, but on this plane going like this, then they're going to every single one of those red lines is going to intersect this one, and it's going to be parallel to this one. And then if you have red lines going this way, like you see there, that are parallel to this one but intersect that one, they'll satisfy it as well. And that's, like I said, same information here. It's just, it's this plane where this is 0 or 180 degrees up there. And then, of course, once you have a plane of parallel red lines, you get the translation perpendicular to it. Okay? And that's also, if you think about it, you know, well, and first of all, both these guys lie on parallel planes which intersect at a hoop. And so any blue line on those planes are going to intersect at a hoop. So, of course, you know there's going to be a hoop and thus a translation perpendicular. And that comes from, you know, say this horizontal red one, as it swings up to infinity, would make a hoop. And same thing with this horizontal red one, as it swings up to infinity, would make the hoop. So the way I show it in the fact chart, because I don't want to be too visually ugly, is I show these, you know, 3 disks kind of swept out on the top and 3 disks swept out on the bottom. Really, I mean just an infinite number of disks on top and bottom, and they're the same thing. You could just show the bottom or you could just show the top. But I think it's clearer to show both. And these disks already have those parallel planes in it, so I didn't want to draw the parallel planes. And then I just draw this black arrow because arrows are prettier than hoops, right? So it's just an arrow right up the center and all these guys. And then, of course, there's a bunch of screws here that I'll talk about in a little bit. Okay? Okay, but the point is that this would be the freedom space, you know, something like this, regardless of, you could imagine it, you know, it's easiest to visualize when this is 90-degree skew, you know, then everything is, you know, these dashed lines are 90 degree from each other and it's all nice and clean. But you could imagine this image would still work if this is, if the skew angle was cocked something not 90 degrees, you could still hinge about it and sweep a disk on the plane, you know, that's hinging about it through this line. And they'd be just kind of cockeyed. But it would still be the same freedom space, right? So that tells you, you know, that, so the whole point is, and by the way, there's no other blue lines. You know, we drew the freedom space. Then normally what I would say is we'll go back and find all the other blue lines that satisfy this condition. You know, that intersect all the red lines somewhere at least once, and there's no other ones. Like the original 2 you stuck in is all there is. There's no other ones. That's all there is. Okay, so then it turns out, and you can see its constraint spaces right there. So then it turns out that if you take a random potato of any shape and stick 2 wires in it, they're either going to be this freedom space if they're parallel, this freedom space if they intersect, or this freedom space if they're skew. And the skew angle, the distance between the parallel lines, the angle between the intersecting things, doesn't matter. They're the same freedom constraint space type. So hopefully you can see that if you have 4 degrees of freedom, there's only 3 ways to get 4 degrees of freedom for a parallel system. Okay? And therefore there's only 3 ways, you know, and there's only 3 ways to stick in 2 sticks. So 6 minus 4 is 2. And they get those 3 freedom space or constraint spaces. Okay, so hopefully I've convinced you there's a finite number in this one and a finite number in that column. Okay, the finite number in the you know, in the third column is much trickier. You know, you can imagine this one has 1, this has 3, this one has 9. Okay, but the way I did that was I said, okay, if there's 3 ways you can get 2 parallel, you know, 2 lines, then let's consider adding a third line with those 3 ways. So let's first look at parallel lines, and again the distance doesn't really matter. And let's think of all the ways we can add a third line and then find its freedom constraint spaces. So I first said, well, if you made it parallel, well, it would be a redundant thing. If you made it intersecting, then you could find a freedom constraint space in the third thing. If you made it on a different plane and it was parallel, do something different. And on a different plane and angled, do something interesting. And then you could have the third one